In this section, we're going to learn how to find extreme values of a function analytically using what's called a candidates test. So first, just a little bit of review, a definition of what extrema are. And that's just the catch-all term for maxes and mins. And in this first section up here, it looks, the notation can be kind of confusing, but it's really not that bad. So f of c, and we say f of c, that means that's the y value at this x value c, is a minimum on this interval I if f of c is less than or equal to f of x. And all I'm saying here is that this y value is less than or equal to all the other y values in the interval. And it's the y value that determines a max or a min. It's the y value that determines how high or low something is. So if your y value is lower than all the other y values on that interval, then you've generated a minimum. And just turning that around, if your y value is greater than all the other y values on the interval, then what you have at f of c is a maximum. In this next section, we're going to look at different classifications of maxes and mins. And we have this word here, absolute, and also referred to as global. They're used interchangeably. And what that means is exactly what it sounds like, the absolute maximum of the function. So if I look at my function that I have graphed over here, my absolute maximum is the highest point that this function attains, which is occurring right here at d f of d. So we say our absolute maximum value is f of d, and it occurs at x equals d. And that is my absolute max because that is my greatest y value. And if you look at this, my absolute min would be my lowest point or my least y value, which is happening here at a comma f of a. And f of a would be my smallest y value. So your absolute max and absolute min look at the entire graph. But I have other types of maxes and mins on this graph. For instance, if we look at this point here, cf of c, if I just look at the points around it, if I just narrow it down and just look right here, I can see that that is a low point. Now, it's not the low point of the entire graph because this point here dips lower, but it is lower than all the points around it. So we would refer to this point as a relative or a local minimum. And I can look at this point e, f of e the same way. If I just narrow the graph down and just look at this portion, I can see that this is a low point compared to all the points around it. So e comma f of e is also a local min. And since this point b comma f of b is higher than all the points around it, we would call that a local max. And I'm calling these points local up here, but you can interchange that word relative. You'll see them called both things. And also just a small technicality, even though I'm referring to these guys here as absolute min and absolute max, they qualify as locals as well. So all of these would be considered local or relative mins and maxes, but the ones that are the highest and lowest points are also classified as absolute max and absolute min. In a few moments, we're going to be asked to find these max and min points. So it's important to notice where they're occurring because we won't have a graph. We're going to be doing it analytically. But one thing I see is these max and min points occur at the endpoints, and that's happening at A and E. If I look at what's happening at points B and D, I can draw a little tangent line, and I see that at those maximum points, I have a slope of 0. So where f prime equals 0 is also where I'm going to find max and min points. And the last place that these occur is what's happening right here at this point c, comma f of c. And I can see because I have a sharp point, that's where f prime is undefined. So that would be at point c. So this is going to be important to know where to look for these extreme values. I'm going to search at endpoints and critical points, and that's going to give me a starting place in order to find my extreme values. In this next section, you have the official extreme value theorem, and all it says is if I have a continuous function on a closed interval, and that's important to note that I have brackets on that indicating a closed interval, then what happens is this EVT guarantees that I'm going to have an absolute maximum and also an absolute minimum on that closed interval. And if it's not a closed interval, then I can't use this theorem. So that's important to pay attention to. And this candidates test is what I'm going to use in order to find absolute maxes and mins. And it's based on what we said above, was that these maximums and minimums are going to occur at critical points. That is where f prime equals 0 or f prime is undefined, and also at endpoints. So that's where I'm going to begin my search, and then I'm going to analyze a little bit further in order to find the smallest value, which gives me my absolute min, and my greatest value, which gives me my absolute max. And I have over here, when you are asked to find an absolute max or min, and you will be given a closed interval, then you're going to do what we're going to call a candidates test that we're going to go through in just a minute. And what belongs in that candidates test are your endpoints and your critical points. Let's go ahead and take a look at a few examples to see how this works. This first example says find the absolute maximum and absolute minimum values of a function f of x on this interval and state where they occur. So a few things that catch my attention on this. When I see this word absolute max and absolute min coupled with this closed interval, what that tells me is I'm going to do a candidates test. I went ahead and brought the instructions from the front in so we could just follow them. Step number 1 says find critical points, which is where f prime equals 0. So I'm going to take the derivative of f and set it equal to 0 and then solve. So when I have a quadratic, I'm going to factor. So I'm going to factor out my common factor of x and then set each factor equal to 0. And that gives me 0 and 8/3. And there's another part to finding critical points, and that's where f prime is undefined. So on here, I'm going to look where f prime is undefined. This particular f prime that I'm dealing with is just a cubic, and it's defined everywhere. So this part over here actually doesn't give me any critical values. So my two critical numbers are just these two, the 0 and the 8/3. And what I do now is I start setting up my candidates table. The x values that belong in here are my two critical numbers and also the endpoints, which are given up in this interval, the -2 and the 3. So out of all the infinite numbers between -2 and 3 that lie on this graph, I have it narrowed down to these four. 0, 8/3 make the cut because they're critical numbers, and the -2 and the 3 make the cut because they're endpoints. What determines which of these is the absolute max and absolute min is the y value. So then when I plug each one of these into my f of x function, it's the y value on f that determines how high or low the point is. So I'm going to take them one at a time and plug them back into this original function. So I'm going back to this f of x. So I'm going to do f of 0, and that's a nice one. So when I plug 0 in, I get 0 plus 4, so f of 0 is 4. And next I'm going to do f of 8/3. So when I take my 8/3 in, I'm going to do 8/3 cubed minus 4 times 8/3 squared plus 4. And I'm going to use my calculator to help me on that one. I get a negative 5.481. And the same thing with the -2. I do f of -2, so -2 cubed minus 4 times -2 squared plus 4. And I get a -20 when I do that. And when I plug the 3 in, I get a -5. So these are the values on the graph of f, and it is the y value that determines how high or low something is. So the highest y value, which is right here, is going to indicate that's my absolute max, and my lowest y value, which is right here, is going to indicate my absolute min. So my absolute max value is the y value of 4, occurs at an x value of 0. And I say my absolute min value of -20 occurs at x equals -2. So your value is your y value, and where it occurs is your x value. Let's take a look at one more example here. And it's the same kind of question. I'm asked to find the absolute max and the absolute min on a closed interval. So I'm going to go through and do the candidates test, which starts by doing g prime and setting it equal to 0, and then find where g prime is undefined. When I do g prime and I use that natural log derivative rule, it's 1 over 2x plus 3 times the derivative of 2x plus 3, which is this 2 right here. If I want to try to find where this equals 0, a fraction equals 0 when the numerator equals 0, and that numerator is locked into a 2. So this will never be able to equal 0, and I don't get any critical points from that consideration. But now I have to look where g prime is undefined. And I know that a fraction is going to be undefined where that denominator is equal to 0, because you can't divide by 0. And that gives me x equals negative 3 halves. However, my negative 3 halves is not in my given interval that's stated to be from 0 to 2, which means I have to throw it out. And once I do that, that actually means that I have no critical values on this graph. What that means is when I go to do my candidates test, the only candidates that are in my table are just the 0 and the 2, which come from these endpoints up here. And to decide which one is the absolute min and which is the absolute max, I'm going to substitute them into my g of x function. So g of 0, taking the 0 up here, is just going to be natural log of 3. And g of 2, plugging a 2 into my natural log function, gives me natural log of 7. And I don't know what natural log of 3 and natural log of 7 are, but what I do know is that natural log of 3 is less than natural log of 7. So this one, natural log of 3, is going to be my absolute min, and natural log of 7 is going to be my absolute max. My absolute min value of natural log of 3 occurs at x equals 0, and my absolute max value of natural log of 7 occurs at x equals 2. What you have to realize on these questions is it's not just about these answers and identifying these, it's about all this work that you show. So just to recap what's necessary on these problems, you have to show me a derivative, you have to set it equal to 0, and you have to solve that. It's good practice to go ahead and show this part as well. A lot of times that can just be done mentally. You don't have to actually show that, but just don't forget about it because sometimes it does give you some critical numbers. This candidates table is mandatory, so you have to make sure you do this and list all the candidates, critical points and endpoints, their values over here, and then make your statement like this. So just remember, it's not just about the answer, it's about the work that you show and the justifications of that answer.